Question number 25, chapter 2 question, chapter 8. A light source of wavelength lambda illuminates a metal and ejects photoelectrons with a maximum kinetic energy of 1 electron volt. This is a light whose wavelength is lambda. A second light source, wavelength lambda over 2, ejects photoelectrons with a maximum kinetic energy of 4 electron volt. So the same metal, we are illuminating this same metal by two different light sources. One of them is a wavelength of lambda, the other one is a wavelength of lambda over 2. What is the work function of this metal? Question is that. We know, according to the equation of energy of photon is equal to hc divided by lambda, wavelength and energy inversely proportional. So the first light has a wavelength of lambda, but second light is a wavelength of lambda over 2, which means if the first light's energy, we say, photon's energy, we say E, second light's photon energy is going to be twice, because energy of photon is inversely proportional to wavelength. So half of the wavelength of the first one, twice of the energy of the first one. Yeah, and first photon, light 1 will have a photon energy E, light 2 will have an energy of the photon 2e. And light 1 ejects electrons with a maximum kinetic energy of 1 electron volt, but light 2 ejects electron with a maximum kinetic energy of 4 electron volt. Because both are illuminating the same metal, so work function is going to be same for each light, metal of the each Y. So then we are going to write the Einstein's photoelectric equation for both light. What is Einstein's photoelectric equation? Maximum kinetic energy of the photoelectrons is equal to energy of the photon minus work function. So now I am going to write Einstein's photoelectric equation for light 1. Kinetic energy of the photoelectrons is 1, so I write in here 1. Energy of the photon is E, yes, it is E. Work function of the metal is HFO, which is the same for both metals. But for both lights, sorry. For second light, energy of the photoelectrons are 4. So 4 electron volt, but energy of the photon is twice 2e. Work function same because they metal. So we are going to find the work function. There are several ways how can we do that. One of them is using system of equations. So I'm going to simplify these e's. To simplify them, I have to multiply the first equation by -2. When I multiply them, -2 times -2 times 1, -2 electron volt. -2 times E, -2E. -2 times -HFO, +2 HFO. Then the second one, right as it is. So 4 electron volt, 2E, -HFO, -HFO. Now, when we add them side by side, this -2 and this +2 will simplify. So 0. So then -2 plus +4, it's going to be 4 minus 2, yani 2 electron volt, left side. Right side, only 2 HO minus HFO is left. 2 HFO minus HFO, it becomes HFO. So we got directly. This is the work function for. And the work function of that metal is 2 electron volt. Next question. Also, this question also asked me frequently, so I'm going to also explain this. 0.5 kilogram mass falls from a height of 3 meters. This is M, this is H. If all the energy of this mass could be converted to visible light of the wavelength 5 times 10 to the power -7 meter, but how many photons would be produced? So when this mass is falling 3 meters down, so of course it's gaining the kinetic energy. When it strikes the metal, all this kinetic energy will be converted to energy of the photons. So now let's calculate this potential energy first. How much potential energy it has at a height of 3 meters on the ground? It's going to be kinetic energy. So that's mgh is the equation for calculating the energy of this mass. When this mass hits the metal, so all this energy is converted to light. So when this metal strikes when this object mass strikes the metal, because all these energy is converted to light, so I have to calculate number of photons, how many photons it emits. First, I have to calculate energy of a single photon, which is calculated by, so h times c divided by lambda. This is one photon. But there are several photons which will be emitted. So if I indicate number of photons with n is number of photons. So to calculate the total energy of the light, I have to multiply energy of a single photon, which is hc over lambda, by number of photons. And this is not quantum level. Sometimes students think that this is quantum level. Or let me write this n by capital N. So to separate them from quantum number. This is number of photons. So then I'm going to insert all this energy, potential energy, which later converted to kinetic energy and also converted to light. So these two energies must be equal to each other. So this is potential energy, which converted to kinetic energy, then all of them converted to light energy, must be equal to number of photons multiplied by energy of a single photon, hc over lambda. Then I will calculate this n, calculate it. I have to transfer hc over lambda other side. So lambda goes from denominator to numerator. C goes from numerator to denominator. H goes from the numerator to denominator. So it becomes mgh lambda divided by hc. After that, you are going to write mgh lambda. This is h, but this h is the Planck constant. C is the speed of light. And you are going to find how many photons emitted from this object. Question number 27 is also another one which is asked frequently. It's more than mathematics, and it's not mostly about physics, a part of physics. Red light of wavelength 607 nanometer produces the photoelectrons from a certain material. First light is red, and green light, the wavelengths are different as you see. Green has a shorter wavelength, produces photoelectrons from the same metal. They're the same metal again. Work functions are same. But this time, kinetic energy becomes 1.5 times of the previous maximum kinetic energy. 1.5 times of red photons kinetic energy. Red photons, photoelectrons emitted from the red light is less energetic than is green. So what is the material's work function? So I'm going to write Einstein's photoelectric equation for both of them. What is Einstein's photoelectric equation? Maximum kinetic energy of the photoelectrons is energy of the photon minus work function. Because the wavelengths are given in both lights, I'm going to write this equation, and energy of the photon, in terms of wavelength. Maximum kinetic energy hc over lambda minus h times Fo is the Einstein's photoelectric equation. Now I'm going to write this Einstein's photoelectric equation for both red light, green light. So red light's photoelectrons energy, say that kinetic energy maximum. hc over lambda 1. I'm going to say this 670 as lambda 1. So hc over lambda 1 minus work function hfo. Then let's write the Einstein's photoelectric equation for green light. But green light releases the electrons with a kinetic energy, maximum kinetic energy 1.5 times of the previous. Yani green light's kinetic energy is going to be 1.5 times of the red. Red one, I said them kinetic energy maximum. Green must be 1.5 times kinetic energy maximum. Is equal to hc over, of course, I'm going to say this second lambda 2, yani green light's wavelength lambda 2 minus hfo. So then I'm going to calculate HFO, but if I want to calculate HFO, so I have to cancel or somehow simplify kinetic energy maximum, because I know HC and lambdas. So kinetic energy maximum are unknown. So I have to simplify that. To simplify that, I have to multiply the first equation by negative 1.5, because if I do like this, negative 1.5 comes in here, so this can simplify. So when I multiply the above red equation, which is in red, by negative 1.5 both sides, mathematically we can do that. So left side becomes negative 1.5 kinetic energy maximum. So multiply hc over lambda 1 by negative 1.5, multiply negative HFO by negative 1.5. So it changes to positive 1.5 HFO. After that, add them side by side. When we add them, this will simplify. What is left only? Negative 1.5 HC over lambda 1 plus HC over lambda 2, yani this term, plus, what is it? Plus 1.5 HFO minus HFO, which is going to be, of course, when we subtract 0.5 HFO. So is equal to 0 because left side is 0. So here is 0. And I am going to calculate HFO, but I see that there is the HFO, but in front of HFO 0.5. So what should I do? First, let me transfer this to the other side. So 0.5 HFO, this negative goes other side as positive. This positive goes other side as negative. So 1.5 HC over lambda 1 minus 1 HC over lambda 2 is going to be 0.5 HFO. As I said, it is the 0.5, but I need HFO, not 0.5 HFO. Once again, multiply by 2. If you multiply both equation by 2, this left side changes to HFO, which I want to calculate. 2 times of 1.5, 3. 2 times of negative 1, negative 2. Then we are ready to calculate HFO. I see that HC is common for both terms. So instead of writing them twice, I'm going to take the parenthesis of HC. Then what is left? 3 over lambda 1 remains in the first term. 2 over lambda 2 remains in the second term. Then insert all the numbers in and then do very carefully calculation. Planck constant 6.63 times 10 to the power negative 4. Speed of light is 3 times 10 to the power 8. Bracket 3 lambda 1 is 670 nanometer, but converted to meters. Minus 2 divided by lambda 2, 520 nanometer converted to meters. And after that, of course, be careful about the brackets. When you continue with this way, very carefully, with brackets, don't miss calculation mistake with calculator, you will get the HFO as 1.26 times 10 to the power negative 19 joule. If work functions ask and given the choices as joule, it's okay. But if given electron volt, of course, we should convert this joule to electron volt by dividing 1.6 times 10 to the power negative 19. Result is going to be 0.8 electron volt. So I think these are enough. The rest of the questions are not that hard, so we can. These 3 questions are only questions which generally ask me every year.